Hey guys, this is for Wednesday. Hope everybody's doing well, and I hope that you're getting to watch all these videos, and hopefully they're not too painful. I will. I still quite haven't figured out how I'm grading the tests yet. I'm trying to hopefully download what you submitted, so that I don't have to grade on a desktop, but we'll see. I think the last person is taking the exam today, and so because of unforeseen circumstances, but hopefully I'll have those back to you either by the end of the week or early next week. Okay, well we've pretty much finished most of chapter 4. Okay, we finished with concavity, and we've talked about maximizations and critical points increasing and decreasing. And if there's more time left in the semester, there's another section that I'd like to hit in chapter 4, which are really some fun problems, some really fun application problems, and we'll see if we can get back to that. But right now, what I want to do is I want to move on into chapter 5. You're like, Dr. Warren, crap, we're in 5.4. Don't worry about it. Don't worry about it. Okay, we're going to go back and pick up some of the other material, but we need to start in 5.4 because we need to really have our exponential function. So much of the material in this chapter depends on the theory of the exponential function, and so that's where we're going to start. So as far as your reading today, I really don't want you reading section 5.4 because my development is radically different than the textbook's development of this. So, but I do want you reading. This sounds silly. The example exercises in 5.4. So I want you looking at the example exercises and going through and looking at those. And when you're doing it, I'd rather have you not just read them. It's better just to like almost have a pencil and paper in hand and just look at it and say, well, how would I attack that? Cover up the solution with your paper, just show the problem itself, see what you can do, and then see what they're doing after you've tried it in your doing it by hand, and see, oh, I didn't understand this. Oh, this is what they wanted you to do. They wanted me to use product rule here. Oh, I didn't understand this. This is this chain rule version of the exponential function. But your homework is in section 5.4, and it's these odd problems right here. 1, 3, 5, 7, 9, 17, 21, 25, and 31. Okay, so here we go. We're going to start and get going here. And we're going to start with something that takes us back to high school with a notation, okay? Because this is going to be important in our definition. We got to remember, like, if we pick a number like 5, and we multiply all the numbers from 1 through 5, okay? 1 times 2 times 3 times 4 times 5. There was a notation back in high school that we used for that, and it was 5 exclamation point, which doesn't mean 5. I mean, doesn't that make sense? Okay, it doesn't mean exclamation mark. We would call it factorial. Okay, this was probably just an easy keyboard thing to hit. Okay, but 5 factorial just means 5 times 4 times 3 times 2 times 1. Or for example, 8 factorial would mean 8 times 7 times 6. On the board already, down to 1. Okay, so that's the first thing that we got to remember. That you give me any number and you say factorial, it just means it's a notation for taking all the natural numbers before it and multiplying them all together. The first ones aren't so bad. I mean, if you think about like 2 factorial, that's just 2 times 1, which is just 2. 1 factorial is just 1. 3 factorial is 3 times 2 times 1, which is just 6. 4 factorial starts getting a little bit bigger. 4 times 3 is 12, 24. 5 factorial, well, it takes a little bit of time, is 120. Okay, and then they start getting big pretty quickly after that. Okay, so that's the first thing that we need. And then this move is probably the most important move with these factorials. If I have 5 times 1 over 5 factorial. If I have 5 times 1 over 5 factorial, well, this means 5 times 5 times 4 times 3 times 2 times 1. Okay? That means 5 times 4, 1 over 5 times 4 times 3 times 2 times 1. But if I look at that, okay, this 5 will cancel that 5, and I'll be left with 1 over 4 times 3 times 2 times 1. But 4 times 3 times 2 times 1 is the same thing as 1 over 4 factorial. So what we see here is that 5 times 1 over 5 factorial ends up being 1 over 4 factorial. And it's not just because it's 5. I mean, we can do this with anything. If we have this, for example, 8 times 1 over 8 factorial, this is the same thing as 1 over 7 factorial, because when we do 8 times 7 times, the 8's will cancel, and we'll just be left with all the rest of them. Or for example, 6 times 1 over 6 factorial is just going to be 1 over 5 factorial. Okay? And it's not difficult math. I mean, it's just more the symbol factorial is what throws us off. Okay? But in general, if you got a natural number k times 1 over k factorial, it's 1 over 1 less than k factorial. Okay, and that result's going to be important when we talk about our exponential function. Okay, so what I want to do now is I want to define the exponential function, and I want to tell you right now, you're not going to like it, okay? Because we're defining it in terms of an infinite sum. We're defining it in terms of an infinite sum. It's like an infinite polynomial, okay? Where it's x's raised to some natural numbers, and there's coefficients in front. Remember what a polynomial is. Probably our simplest example is ax squared plus bx plus c, which are parabolas. mx plus b, okay, which is our lines that we have there. Okay, well this parabola, this infinite polynomial that we're going to talk about, we're going to call it e to the x. We're going to call it e to the x, where e is a number I know you've run into before, but this is going to be the definition of this function e to the x. Okay, so this is a function. I mean, I could use f of x, but I want to be a little, so maybe I'll call it g of x. G of x is equal to e to the x, and it's defined to be this. It's 1. I mean, Dr. Warren, e to the x isn't 1. No, I know. Then plus x. And you're like, well, Dr. Warren, that doesn't look so bad. Now this is when it starts getting bad. We've got this coefficient, which is 1 over 2 factorial, which we know up here is just 1/2 from what we were doing earlier, times x squared. And then there's a 1 over 3 factorial times x cubed, and 1 over 4 factorial times x to the 4th. Now, if we blew this out, this would be 1/6. By what we're doing up, this would be 1 over 24. Now, here's the kicker. This keeps going on forever and ever. And so that's what makes this complicated. But it's okay. We are not in the business in Math 205 of talking about what we call an infinite sum, an infinite series, okay? What we're talking about here is where we just want to get an understanding of what e to the x is, okay? Now you can take out your calculator, and if you wanted to get an approximation to e, you could get out your calculator, okay, and you could put in e to the 1, which would just be e, which would be, if you can remember, the first 2.71, and then we get a lot of decimal places after that. But if you wanted to figure out how you could actually get this number, it would be just wherever you see an x, you would put a 1. So it'd be 1 plus 1, that gives you the 2, then plus 1 over 2 factorial, 1 squared, which is just 1, plus 1 over 3 factorial, 1 cubed, and then this keeps going on. Now here's the kicker. We can't really add up it infinitely many times, okay? But if you do this and you just simplify this, this would be 1 plus 1 plus 1/2. If I multiply that out, 1/6 plus 1/24. And even if you just stop there, you're already going to start getting that 2.71. Okay, but that's not what's most important in calculus about this. It's not just finding e raised to some power. In calculus, we're talking about functions. And calculus is about what again? My back is turned to you. And hopefully, like Dr. Warren, it's about limits, derivatives, and integrals, oh my. Say that again. Limits, derivatives, and integrals, oh my. So we're going to be wanting to talk about the derivative of e to the x. I guess before I do that, let's look at e to the 0, because I think that's one value we can actually get. Exactly. E to the 0, wherever I see an x, I'm going to put a 0. If I do that, I get 1 plus 0, then plus 1 over 2 factorial, 0 squared. But 0 times 0 is 0. 0 times 1 over 2 factorial is going to be 0. And you can see wherever I put a 0 in each one of those terms, they're all going to evaporate like that. And this thing's going to collapse like a house of cards. And we're just going to be left with e to the 0 is equal to 1. We're just going to be left with e to the 0 is equal to 1. And so this is one of the few numbers that we can actually figure out exactly what e to some power is. So e to the 0 is 1. Okay, now what I want to do, and I think I might have to erase a good part of what I have up here, or I guess maybe, well, let me go, I think maybe I'll erase this. So I'll need this space. Okay. So let me get this out of the way here too. Cramping our style. It's cramping our style. Let's just put that result up here. So this is one of my first results about e to the 0. Okay, so now calculus is about limits. Derivatives are defined in terms of limits. Let's take the derivative of e to the x. Now it takes a little bit of work to justify in some upper level calculus classes that you can distribute a derivative across an infinite sum, but you can. So this would be equal to the derivative of this guy plus the derivative of this guy. We can pull the constant out. Like for example, if you had 3x squared plus 7x plus 2, and I ask you to take the derivative of it, you already know we have a constant multiplier rule that says we can just go, this is like 2 times 3, 3 times 2 times x. We ignore the derivative of x is 1, and we know that that's 0. We do this instinctually, so we can put this here. Now, I want the derivative of x squared. The derivative of x cubed, and this is just going to keep going on forever and ever. I'm regretting putting the 6 here because it's more work. Okay, so that keeps going on forever and ever and ever. Now you guys help me out. What's the derivative of x to the k? What's the derivative of x to the k? Jonathan, what's the derivative of x to the k? And hopefully you're like Dr. Warren, that's k times x to the k minus 1. So let's use that flashcard, our derivative flashcard, to take the derivatives of all of these powers of x. The first one's not so bad. What's the derivative of the constant 1? And hopefully everybody's like, Dr. Warren, that's 0. Well, what's the derivative of x? Well, that's 1. Well, what's the derivative of x squared? Remember this guy's hanging around. 2 times x. What's the derivative of x cubed? And hopefully you're like, well, Dr. Warren, that's 3x squared. And if we keep doing this, and then we'd have a bunch of derivatives going on after that. We'd have a bunch of derivatives going on after that. So all I've done is I've got this definition of this infinite sum that's representing my e to the x. It's an infinite polynomial, okay? And then all I've done is take the derivative of both sides. Okay, two kids come complaining to you. What do? Okay, never mind. Okay, you take the derivative of both sides. I've distributed the derivative across. We have our sum rule, okay? It's a little bit of work to guarantee we can do an infinite number. And then we're just using a power rule over and over and over again. We're just using our power rule over and over and over again. But now I want you to look at these coefficients in front of each one of these terms. Like, for example, let's just look at this. We've got 4 times 1 over 4 factorial, but that's the same thing as 4 times 1 over 4 factorial. And this is what we were talking about earlier. This is, let's just do it one more time. Just using the definition of what that notation is. Remember, it doesn't mean 4, it means 4 times 2 times 2. This guy cancels this, and we get 1 over 3 times 2 times 1. Ooh, sounds a little ominous out there right now with the thunderstorm. Dr. Warren, that sounds easier than listening to you. Which is 1 over 3 factorial. Or in general, where I've got the k times 1 over k factorial, it's just 1 less than that. Like, for example, the 6 times the 1 over 6 factorial is just going to be 1 over 1 less than 6 factorial, which would be 5 factorial. So in all of these things, this would be like 2 times 1/2. So this would be 0. This is 1. These guys actually cancel. So I'd have an x. Here, this would be 1 over 2 factorial. That's what these two guys would do. And then I'd get an x squared. And this would be a 1 over 3 factorial, x cubed. This would be a 1 over 4 factorial, x to the 4th. This would be a 1 over 5 factorial, x to the 5th. And this keeps going on forever and ever and ever. And you're like, okay, Dr. Warren, what's the big deal? I mean, why are you dragging me through this? Okay, well, calculus is about derivatives. So we've got e to the x. The derivative of e to the x was this, which was this, which was this. But if I look here, this is 0 plus 1. I get that the derivative of e to the x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th. Now, we don't have the term there. We didn't put it in, but what would the next term be? Just use your ability to take a sequence a little bit further. What would the next term be after that? And hopefully you're like, well, it'd be 1 over 6 factorial x to the 6th. And this would keep going on and on and on and on. You're like, well, Dr. Warren, I know there's something to this. There's something nagging at me in the back of my head. But if you look at this, and look at this. Dr. Warren, what are you doing? Look at this. This is what we got by taking the derivative. This line right here, and let's look here. We've got a 1 and a 1. We've got an x and an x. We've got a 1 over 2 factorial x squared and a 1 over 2 factorial x squared. In fact, if you look at every single term, it has an identical match in the series below. Like, whoa, Dr. Warren. But this series is e to the x. But this is the exact same series. It's also e to the x. Where it converges, which we can show is for all real numbers, okay? So what we really argued, justified, not proved, justified, is that the derivative of this function, unbelievably, is itself. The derivative of e to the x is e to the x. It's an amazing function. It's a remarkable function. Like for example, the derivative of x to the fifth, you're like, that's not hard, Dr. Warren. That's 5x to the fourth. But the derivative of the exponential function is crazy. It just equals itself. As complicated as the function is, it's got the easiest derivative of all the functions. You don't even have to be sober to remember the derivative of the x. What's the derivative of the x? And you're like, I do. Well, I think that, I can't remember. What did you say? Well, what's the derivative of the x? E to the x? You're right. It's e to the x. It's got the simplest derivative of all the functions. So the function, and let's make this a flashcard. Let's make this a flashcard. Okay. I'm not so much going to worry about, ooh, I think we lost power there. That doesn't usually happen. So I don't know quite what to do. Let me see how dark we are now, see if you can see anything. I think I'm going to continue. Whoa, we got power back. Okay. I'm not sure my computer's going to be back. Okay. Oh, hope I didn't lose everything on my machine. Oh well. Okay, back to where we were. Okay, our flashcard, our first flashcard. Okay, if this is the front, this is the back. If f of x is equal to e to the x, then f prime of x is equal to what? And hopefully you're going to write down on the back is e to the x. Okay, the derivative of e to the x is e to the x. Another way to write this, and you could use this as your flashcard too. The derivative of e to the x, the derivative of e to the x, that would be the front of your flashcard, and that would be the back of your flashcard. So the derivative of e to the x is e to the x. Say that with me. You say it first. The derivative of e to the x is e to the x. Now let me just show you how to use this in a problem. Like for example, suppose I've got this function g of x, which is equal to x squared times e to the x. Like, Dr. Warren, I'm not plotting that thing. I didn't ask you to plot it. Okay? I just want you to take the derivative of it. You're like, I don't want to take the derivative of it, Dr. Warren. Come on, this is calculus. So if I'm taking the derivative of this, okay, it would be the derivative of this, x squared times e to the x squared times e to the x. Okay, so you help me out. What rule do I want to use when I hear the word times? And hopefully you're like, Dr. Warren, product rule. So it'd be the derivative of the first, and I'm going to do this in 2 steps. I know you won't. The derivative of the first times the second, plus, remember that's the connection sign in this rule, the first times the derivative of the second. Okay, now hopefully everybody owns this after our last test. What's the derivative of x squared? You're like 2x e to the x. Now, what's the derivative of e to the x? Okay, it's the simplest derivative ever. It's just itself. So we just put in e to the x. We just put in e to the x. Now, if you were trying to analyze this for intervals of increase and decrease, local maxes, local mins, at this point in time you're going to want to factor. At this point in time you want to factor. Okay, so I'd probably factor out an e to the x. You can definitely have that. You could also, there's an x that we can factor, and then we'd have a 2 plus x. Then we have a 2 plus x. Okay, so but you can see that really taking the derivative of the exponential function is one of the easiest things to do in the world. Even though the exponential function itself is quite complicated and is used to model so many different things, its derivative is not so bad. Okay, now what I want you to do is I want you to pause the video, okay, and then I'm going to erase, and then we're going to talk about what happens when this is not just x itself. Okay, so that's what I want you to do. I want you to pause the video, and then I'm going to erase, go get a drink, and then come back and start the video. I don't know how to splice videos, guys, so you get to enjoy seeing my rear end while I erase. Okay. I guess I'll leave that there. Okay. Now what would, couple things. This is the flashcard we're gonna need, okay? If I've got f of x to the fifth, and I want to take the derivative of that, think about the flashcards you want. So actually, you guys go ahead, try to take the derivative of that, see what you get. Write it down, see if you can remember your flashcards, okay? And hopefully you're like with Dr. Warren, we're using our chain rule power flashcard, which means this would be 5. We'll leave the stuff on the inside the same to the fourth. Now we can't forget the part of the chain reaction, okay? That this causes this chain reaction of this F prime to also be there, okay? And that's going to be really important. This is going to look like a little bit like an eggshell game, okay? Where you're at the beach and somebody's trying to steal your money, okay? When we're doing this. Now I've got e to the x. So if I'm looking at like e to the, forgive me, apple. Well, it's a function, so wherever I see an x, I put an apple. So this would be 1 plus apple, that real number, plus 1 over 2 factorial apple squared, and I think you're getting it, 1 over 3 factorial apple cubed, and that would keep going on forever and ever and ever. So whatever I put here, whatever I'm putting in for x, I'm putting it in all those different x locations. Okay, now this is the thing that's going to disappoint us, okay? Because the thing I'm going to put in here is not going to be an apple. The thing I'm going to put in here is a function, e to the f of x. Now it is like the apple. It is like the apple. Wherever I see the apple, I'm going to put an f of x. So it would be 1 plus the apple, but my apple's f of x, plus 1 over 2 factorial, apple squared, plus 1 over 3 factorial, apple cubed, plus 1 over 4 factorial, apple to the fourth. I almost drew the apple. And this keeps going on forever and ever and ever. Okay, now what we're going to do is we're going to take the derivative of this side, spank this side with the derivative. Okay. 2 kids come complaining to you, 2 children come complaining to you, okay, your children, and they're saying this one did this and this. Okay, what do you do? What do you do? You spank both of them because you don't know which one's lying. Okay, you spank both of them. And then they won't come and complain to you anymore. They'll always take their discipline to mom. They'll always take their discipline to mom. This is what I learned. This is what I learned. Okay, okay, sorry. Okay, enough of that. Okay, hopefully I won't get my children taking it away. Okay, now let's take the derivative of this. The derivative of this side is going to be equal to the derivative of that side. And I can distribute the derivatives across here. But wherever I'm taking this derivative, I've got to remember my power rule. Wherever I'm taking that derivative, I've got to remember my power rule. So the derivative of this would be 0. Distributing the derivative, this would be an f prime of x. I don't have anything else. Here, kind of like what we were doing down in here when we take the derivative, I get this 1 over 2 factorial, 2 times f of x. Now remember, it's a chain rule, so there's going to be an f prime of x coming off of that too. Bring down the 2, subtract 1, it's just the 1, and then we got our chain reaction part. We're really using this flashcard. The derivative of f of x to the k is k f of x to the k minus 1 times f prime of x. We're always going to have that f prime of x with all of these terms. So this would then be 1 over 3 factorial, that's just a constant, f of x squared times f prime of x, and this keeps going on and on. I'm not even talking now. And then the last one would be, I know there's a lot of symbols going on the board here, but don't worry about it. And that would keep going on forever and ever and ever and ever. Okay, now what I want you to do is I want you to copy that down. I want you to copy that down. You can pause me and copy that down. And then what I want you to do is I want you to notice that in every non-zero term, there's an f prime. There's an f prime here, there's an f prime there, 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 and there'd be an f prime there, and for all the rest of the terms there would be an f prime. So let's factor that f prime out. Let's pull it out of all of the terms. Let's pull that out of all of the terms. And if I do that, I'd be left with 1. Now remember the game we were playing before, that 5 times 1 over 5 factorials, 1 over 4 factorial. So these guys actually cancel. We've already pulled this f prime here, so this would just be an f of x. The 3 times 1 over 3 factorial is 1 over 2 factorial. F of x squared, which is just the f prime, again, is gone here. This term, these guys are going to be a 1 over 3 factorial, using that property that we used earlier. F of x cubed, and then that f prime has already been pulled out. This one's going to be a 1 over 4 factorial, f of x to the 4th, and again, that f prime's backed out. Again, I didn't put in the next term, but if you were just using your intuition, what would you guess the next term would be? I mean, it's an infinite expansion, and hopefully you're like Dr. 1 to be 1 over 5 factorial, f of x to the 5th, and the next term would be 1 over 6 factorial, f of x to the 6th, and so on and so on and so on. Okay, Dr. 1, who cares? Well, you're going to care, because if you look up here, do you really want this to be the flashcard? Do you really want this to be the flashcard? You're like, no, Dr. 1, I don't want that to be the flashcard. Okay, if I look up here, look, this, just look at the thing inside these brackets, okay, and look at what's here. There's a 1 and a 1, an f of x and an f of x, a 1 over 2 factorial, a 1 over 2 factorial. We get it, Dr. Warren. They're all the same. All of the terms in this infinite sum is the same as the ones in this infinite sum here. So what the flashcard ends up being is we have this f prime of x, but all of this stuff, and I guess I'll use another color. Now I'm teaching like a real pro, and I'm using another color. All of this is the same as this, and this is equal to e to the f of x. So all of this is equal to e to the f of x. Dr. Warren, that's a mess. That's a mess. Do you think you could clean that up for me? Yeah, sure. Let me get rid of all this stuff down here. Let me get rid of all this. So remember when we talked about chain rule, we talked about fetuses and moms and pregnancy and all that. So if we're looking at this, if we have a pregnant exponential function, okay? Now again, it looks a little bit different because we got a base and an exponent. But if we want to take the derivative of e raised to any other function, what we've kind of justified here is that it ends up being just e raised to that function. You mean, Dr. Warren, I just write down exactly what I'm taking the derivative of? Essentially. Times f prime of x. So if you have e raised to any function, it's just e to that function times the derivative of that function. And this is a really awesome flashcard. This is a really awesome flashcard. So the front of your flashcard would look like this. That would be the front of your flashcard, the derivative of e to the f of x. And on the back of your flashcard, I want you to have e to the f of x times f prime of x. E to the f of x times f prime of x. Okay, now again, our justification was in terms of this infinite series, or this infinite sum. It's a polynomial. It's a polynomial this time in terms of f of x. And I know, I'm the only one who really thinks this is really, really cool. But this is really, really cool. Okay, so now let's talk about trying to use this flashcard in some of the stuff that you're going to do your homework. So let me clean this board. What's the derivative of e to the x? What did you say? Did I hear e to the x? I so badly want to play music. I'm not quite sure how I can do that without getting a copyright thing. So I want you guys to wake up. Okay, stand up, stretch, we're in the home stretch. Okay, so now I just want to look at a couple of examples for us. Like for example, suppose I had this bad boy. Suppose they said, oh, f of x, here's my function, is equal to e. Now, of course, this f of x is different than the one that we have down here, is equal to e to the x squared minus 1. And what they want us to do is take the derivative of this. What is the derivative of this? Well, you're taking the derivative of this. But now you've got your handy dandy little pocket knife flashcard here. Who's the f of x? You're like, well, Dr. Warren, the thing that up in the exponent is the x squared minus 1. So it's just going to be, using our flashcard, e to the f of x, x squared minus 1, notice that's my f of x, times the derivative of that exponent. Well, hopefully you're like, Dr. Warren, I own this. The derivative of x squared minus 1, 0, 2x. So this is just e to the x squared minus 1 times 2x. It's just that simple. Like, for example, suppose you were asked to take the derivative of e, x to the 4th plus 3x squared plus 2x plus 1. Like, Dr. Warren, do I have to plot that? No, you don't have to plot that. This would be a beast to plot. But if I want to take the derivative of it, who's the f of x? Well, it's all of this. So it's just e raised to the f of x. Now I'm not writing this times the derivative of this, Well, this would be 4x cubed, 6x plus 2. 4x cubed, 6x plus 2. So you take one of the most complicated functions, e to the x, and it has one of the simplest derivatives. Okay, so now I just want to look at a couple more examples, and then I'm going to let you go. Some of these are from the book. They're similar to the ones that I've assigned up here. My marker seems to be dying, so let me grab this one here. Let's look at this. F of x equals x squared plus 1 times e to the minus x squared. So now what we're doing is we're going to do some math karate. Okay, we're going to sequence our moves together. We're going to have our whatever punch. Okay, then we're going to have our side kick. Bam. We're going to use multiple rules all together. I want to take the derivative of this, which would be like taking the derivative of that. But when you say this, you say x squared plus 1 times e to the minus x squared. So you know you need to start, when you're attacking this thing, with your good old product rule punch. Okay, so whoa. Okay, so we do that. It's the derivative of the first. Now I know many of you don't have to do this, but I'm going to do it in 2 steps. So it's going to be the derivative of this guy times the second. What's the connection sign in product rule? Plus the first times the derivative of the second. So I'm hoping everybody could at least get that far. But am I done? Am I done taking derivatives? And you're like, no, you still have to do that. Well, how many people are terrified of the derivative of x squared plus 1? Hopefully nobody. If I did that, I would have 2x. This guy's just hanging around. This is x squared plus 1, okay? Now we've got to take the derivative of this guy. Now I have purposely erased the flashcard, okay? But who's the f of x? And hopefully you're like minus x squared. So if I was taking the derivative of this, it would be e to the f of x, that exponent, then times the derivative of that exponent. And again, I'm just using the flashcard. Where in this case, the f of x is that guy there. Now hopefully everybody could take the derivative, of minus x squared. That would be minus 2x. And then we'd clean this up if they needed us to. If we were looking for intervals of increase and decrease, that kind of stuff, we'd have to factor this, find critical points and all that. But this is basically the kind of stuff. One thing that screwed me up, and I guess I'll just take care of it here, it's really simple. If you got the derivative of e to any power, like that, where it's just minus 7 times x, this is just using that flashcard, that times the derivative of that, but that's just times minus 7. So in general, e to any m times x, the derivative is just m times e to the mx. It's just something quick. Sometimes you don't want to have to go through actually going through using the flashcard. Now notice this is just a constant times x. I don't want you using it for everything. All right, so I want you guys using our new flashcards. Derivative of e to the x is e to the x. The derivative of e to the f of x is e to the f of x times f prime of x. Say that. E to the f of x times f prime of x. And I want you using those to work on those flashcards up there. Work on those flashcards up there. Work on these homework problems up there. Again, they're all odd. They're odd. We'll probably have a quiz next week. I'm not sure exactly when or exactly what content, but we'll probably have a quiz next week. Remember, you have a WebAssign. We have a WebAssign due on Friday. All right. Thanks, guys. Have a good day.